Okay. We're all good now, I think.
Yeah.
Okay.
Perfect. Thank
All
you
right.
so much.
All right. Good morning, everyone. We're very happy to welcome Miguel Angel Fernandez Torres, which has a name even almost as long as mine.
Yeah, that's true.
So Miguel did his PhD on modeling of attention and for visual attention, and now he's at the image processing group of University of Valencia, working at the intersection between machine learning and climate sciences. And today we're going to hear about recent work on forecasting.
It's mainly detection. A bit of gut feeling plus detection. Now yeah. I can tell you more.
On drought events. Yeah.
Okay.
The floor is yours. Thanks for being here.
Thank you so much. Thank you for the invitation. As Vivian said very well, I don't know which screen do you prefer me to be using? The one you, okay, maybe I can stay here and I can use this one, for instance. As Vivian told, very nice. I did my PhD in Madrid in multimedia and communication.
Actually, it would be nice if you're closer to the.
Okay. In order to keep the audio. Okay, so I will stay here. I did my PhD on multimedia and communications in Universidad Carlos III of Madrid. My PhD was about visual attention modeling on conventional videos. The objective was to perform anomaly detection to use visual attention for anomaly detection in video surveillance videos. And then after this not very long, still path or way, after finishing the PhD, I arrived to Valencia, where I have been as a postdoc during 3 years now at the image and signal processing group from the image processing laboratory. This is part of the people, part of my colleagues at the University of Valencia. The group has, the number of people in the group has significantly increased during the last 2-3 years. Now we are around 50 people, and we are mainly involved in projects related with Earth observations, climate variables, or related or with the ultimate goal of helping mitigating climate change. Within this group, thanks to the opportunities Professor Gustav Camps Valls is giving to me, I'm having the possibility and having the opportunity of co-supervising with him some PhD students, Maria, Jordi, Monsieur, who is not in the picture, but now I will present you some of the research they have been doing. And today, what I'm going to do is to talk about the extreme event monitoring, challenges and strategies we should take into account when addressing this task. This is what I'm going to introduce right now in the first part of the presentation. Then, after introducing these challenges, I'm going to present 3 research works we have been addressing during the last months. The first one is about the Earth surface gap filling using satellite imagery. And the second and the third ones are about drought detection. The first one is about using domain knowledge. It's a domain knowledge-driven drought detection system by combining a drought index, the standardized precipitation evapotranspiration index, together with climate observations, precipitation and temperature. And the second work about the drought detection is the research I'm conducting. We are trying to solve or to address drought detection in a completely unsupervised way. Then I will finish also presenting you a toolbox, a framework, a generic framework for extreme event monitoring we are currently also developing and trying to foster, and some take-home messages. So let me begin by introducing the difference between the different tasks. I'm going to talk a little bit about them today. The first one is detection. Detection, the idea is that given several climate variables or satellite observations, the objective is to try to get a signal to detect those spatial-temporal locations. We are going to get time series of spatial maps at which the extreme events have happened. Today, I'm going to be mainly focused on rocks, which is our research, but the detection could be addressed, or it has been done also in the literature for wildfires, for floods, for other kind of streams. At the same time, when providing the signals, we can discover underlying patterns and correlations in these variables when the events are happening. In contrast to detection, or in order to make the difference between detection, forecasting is not only detecting those moments at which streams are happening, but also to anticipate future streams. We want to model what's going to be the evolution of these variables of this Earth surface when a stream is happening, condition on extreme conditions, on extreme climate conditions. It's not only important, the detection and forecasting, but also the assessment of the impacts of streams. The idea is that given these streams happening, we would like to predict and to analyze the consequences of these streams from a social, from an economic, or from an environmental perspective. What are the effects caused by streams when they happen? And last but not least, is very, very important, given that our final goal will be to try to deploy these systems in real scenarios. It's very important to trust in these systems. So in order to trust in these systems, what we need is to explain, we need to understand how they are providing automatically these predictions. And to this end, we would like, or it's very, very important to consider explainable AI methods. Challenges. Here, there's a list. Probably there are more challenges to face when dealing with extreme event monitoring and understanding, but here there's a list of challenges we are currently facing on our research in Valencia. First of all, although it's been a great effort by authors, by the community, of preparing better databases for extreme event monitoring, there's still a lack. There are a lot of databases in the literature, but most of them, they are not considering spatial-temporal dependencies at the same time. Maybe they are only based on still images, or they don't have a lot of events because we don't have a lot of annotations. We don't have a lot of curated data. So it's very important to contribute with new databases in order to address these tasks. This data, however, we have some issues with this data because we have some missing information, we have gaps, we have, in the case of satellite imagery, we have clouds, we have artifacts. So somehow we need to interpolate, we need to gap fill, we need to improve the quality of this data when dealing with it for solving these tasks. Also regarding the labels, the annotations for the streams, the description of some of the streams is quite complex, or some streams as droughts can be described from multiple perspectives. Because of that, the labels of the annotations we have are weak, or they are noisy. They don't usually correspond exactly with those locations or those time steps at which streams are happening, and we need to deal with this issue when proposing strategies for monitoring systems. The architecture design and the spatial-temporal receptive field is also another challenge. In the same way that extreme event indicators or drought indicators, in our case, are taken into account or are being computed at multiple time scales, monthly, 3 months, 12 months, we need also to consider this receptive field when designing architectures for modeling, for using machine learning to monitor these streams. The evaluation procedures and metrics are also important. How we are going to evaluate the performance of these methods, especially when we lack of labels, when the information we have is not very, very precise. Explainable AI methods in the literature at the moment, they are mainly attribution-based, or we have attention mechanisms. What they provide us is with saliency maps, highlighting those spatial-temporal locations at input features which are more relevant in order to provide, which have been more relevant in order to provide the prediction at the output. However, if we have tons of variables at the input, if we have many spatiotemporal locations, these explanations provided, these saliency maps provided by the explainable AI methods, are still not meaningful for experts, and how we need to find better ways of aligning these saliency maps with the opinion or the explanations, the knowledge provided by experts in this field. If it's already difficult to model individual streams, modeling compound events, such as a compound event of heap width plus drought, is even more challenging. It's something we are trying to do at the moment. In one of the projects I didn't introduce the projects I'm being part of in Valencia, the USMILE project, which is a generic project about machine learning for earth sciences, the XIDA project, which is about artificial intelligence for extreme event monitoring, extreme event attribution. And I'm also taking part in a project of the ESA, which is called Deep Streams, which is about Earth surface forecasting, trying to understand compound events of heat waves plus droughts. So it's something we are also trying to do by, we are going to provide very soon a new database in the literature with minikubes worldwide in order to study these compound events. And we want to perform not only forecasting, but also explainability in order to understand how these compound events work. Impact assessment, that's a challenge itself. Generic versus location-aware models. Do we need, or it's necessary when modeling streams, is the same model, a global, a generic model suitable for all locations worldwide? Or however, we should adapt our models to specific locations we apply in these models for extreme event monitoring. Probably depending on the properties of the locations around the world, we are going to need to adapt slightly our systems in order to obtain better performances. This is something we are also trying to address with the research I'm not going to introduce today. The integration of expert knowledge, it's something we are going to see in one of the works I have brought you to today regarding a hybrid model for drought detection in Europe, the combination of expert knowledge encoded by drought indicators with raw observations, climate or observations. And finally, it would be great, but also very challenging to get a generic framework in order to cope with all extreme event types. That's something we are also trying to pursue, but we know it's a very challenging ultimate goal to take into account, to try to integrate or to try to model all the streams all at once, all at the same time. Monitoring everywhere, all at once. Okay, so let me begin now. Once I have introduced the challenges we are facing regarding extreme event monitoring, let me begin with the first research work I'm going to present today. It's a work about Earth surface gap filling. It's the first stage of Maria's thesis. It has been recently submitted to a journal. It's currently under review. The purpose of the thesis of Maria, in supervising with Gustavo, is to perform forecasting on satellite imagery. The thing here is that when we started performing forecasting on this satellite imagery, we realized that we had a lot of clouds, a lot of artifacts, that the images, the quality of the images was not very accurate, was not very good. So we made the decision as a prior stage to the forecasting of performing Earth surface gap filling. And what we have been doing in the first part of her thesis is to develop a generative architecture, a spatiotemporal generative architecture based on convolutional LSTMs and following a generative adversarial strategy in order to model the temporal evolution of Sentinel-2 time series in Europe, in order to gap fill these locations, these clouds, these artifacts we have in satellite imagery in order to improve the quality of the images. We have paid attention when conducting this research to the architecture, but also to the evaluation procedures. We have seen in the literature that most of the times the evaluation procedures are reconstruction or perceptual based. But however, one of the challenges we have when performing gap filling, when evaluating the performance of gap filling systems, is that the thing is that we don't have a proper ground truth. We don't have a target because the locations we are completing, the locations we are gap filling are occluded. And because they are occluded, we don't have a proper target can be compared with the output of our systems. We need to find ways of more suitably evaluating these systems. So we have relied on distribution-based metrics to design. And last but not least, we have also evaluated the quality of the data in order to perform a very, very simple forecasting task as a prior to the second stage of her thesis, which will be about forecasting. This is the system we have. I don't know, are you familiarized with RANs? Okay, so more or less I can skip this. We have a generator, it receives, because it's a sequence-to-sequence translation gap filling system, so it receives the complete sequence of satellite imagery. It's a noisy sequence, and it's going to be the noise thanks to the strategy, thanks to the adversarial strategy. When using a discriminator, we are going to try to improve the quality of the generated samples here by removing the clouds and artifacts we have attained. Now I will give you more details on this architecture. So the architecture is receiving the visible RGB channels plus the near-infrared channels. We have 4 input channels, and also we have 10 time steps. The sequences are composed of 10 time steps. This is because of the EarNet 2021 database we are using for the experiments. It considers 10 context frames, and we are performing gap filling on the context locations. Then, if I go here, this is an example of a minikube in the EarNet 2021 database. It is that we have the satellite imagery, also the climate variables. The climate variables are not being used at the moment for gap filling. They will be used at a later stage for forecasting. We are only relying on the satellite imagery. We have 10 context frames we are using for gap filling, and we are leaving the target frames for the forecasting task. So our research, our experiments on this first part. And then in this EarNet 2021 dataset by Christian Requeña Mesa et al., we have different tracks for the experiments. We have a generic train set for training purposes, and we have an independent identically distributed test set and an auto distribution test set in order to see how is the performance of the system, in order to evaluate the performance of the system on locations sampled on minikubes sampled on the same locations as the training set, and also on minikubes sampled at different locations from the training set. So given this database, we are dealing with a completely spatiotemporal architecture. We are going to introduce both convolutional LSTMs in the generator, encoder and decoder, but also, we are going to introduce convolutional LSTMs in the discriminator in order to take into account the spatiotemporal dependencies. And now, because of the results I'm going to present, we are going to see how important it is to consider spatiotemporal dependencies when achieving better performances on gap filling. The discriminator is based also is built on the basis of the well-known PAT scan, but being adapted in order to introduce these convolutional LSTMs. And we are going to follow an unconditional strategy in order to learn this, or in order to learn how to differentiate between generated samples and real samples in order to provide feedback to the generator. It's an unconditional setting in such a way that in the original PAT scan, if I remember well, we were conditioning the real and the generated samples to a noisy sample. But here in this case, we are removing this condition, and we are going to see that this, because of an ablation study, this achieves better performances. Let me continue then. If you have thoughts, please feel free to ask in the end about the architecture design. These are the first results we have got on Earth surface gap filling. The idea is that we are going to evaluate from a first perspective, the architecture, from the perspective of the reconstruction. How well the architecture is preserving the information we had already available in the image, the information which was already clean. We are still not talking about the gap fill regions, but we are talking about those regions at which we can perform a comparison. We have a target to compare with, to compare the outputs of our system with it. In order to measure the reconstruction error of the system, we have used the two well-known metrics, the peak signal to noise ratio and the structure similarity index measure, in order to see the higher the value of these scores, the better the performance. And in order to compare the performance of our system, whose generator is completely spatiotemporal, discriminator is spatiotemporal as well, no condition discriminator. We are not using noisy images in order to condition the clean and generated images when training the discriminator. And for the case of paired data, here about the paired data is when we make use of clean and generated samples from the same location. If they are from the same location, we talk about paired data. If we make use of clean and generated samples from different locations, we don't talk about paired data. This would be this condition. What we are doing is not to consider paired data for training this discriminator, but still the samples are taken from adjacent tiles. So the idea is that we have a minikube at a particular tile, and we are going to take a different location, but from a nearby location, not to be very, very far, or not to change a lot the content of the minikube when performing this discriminative approach. So we are going to compare our model, the sequence-to-sequence model, with 4 models, the pitch-to-pitch model in the literature, which is spatial, which is taking the condition discriminator and the paired data, and with these 3, model 1, model 2, model 3, which are different ablations of the final architecture. All the 3 models have a spatiotemporal generator. The discriminator is still spatial, and we are considering or removing these conditions for the condition discriminator and using or not minikubes from the same location, using or not paired data. Based on this study, we see that in terms of quantitative results, our model outperforms of these models. But now I'm going to show you with the example minikube what's the difference in terms of qualitative performance. If we go here to this minikube example, on the first row, what we have, first of all, is the land cover map in order to get an idea about what is the content of the scene. Here's the legend. So mainly we have in this example minikube cultivated areas, coniferous tree cover, and we also have some artificial surface and constructions. We see that we have some frames which are almost completely occluded, the second and the 5th one, also the last one, and we have some clouds in the middle, some slight artifacts. We see that the model in the literature, the pitch-to-pitch model, is not, because it's only modeling spatial dependencies, is not able to properly reconstruct those occluded locations. For the first model, at which we are changing the generator from spatial to spatiotemporal, we are keeping still the remaining of the configuration of the pitch-to-pitch. We are able to achieve better performances, but still on those occluded samples of those occluded frames, we see that there is a subtle change in colors. Still, we are not able to complete the evolution of the entire sequence. It looks pretty nice. When we see the third row, I didn't mention before, is the NDVI time series. We see that there are some subtle differences in coloring activations when computing this NDVI, and it's because it's not reconstructed still well, the sequence, because of the lack of spatiotemporal dependencies in the discriminator. The model 2 is a failure model. We introduce it here only to you to see that when the thing here is that still we keep the spatiotemporal generator, spatial discriminator, but now we remove this condition of having clean and generated samples from the same location. Now we have clean and generated samples from different locations. When still conditioning these samples, but from different locations, we come with the failure model. It's not working well, as you can see. It's not replicating, it's not reconstructing the structure of the elements in the scene. It's not performing well. The only thing it tries to maintain is the balance of colors in the image. So this is a model failure. It's one of the ablations which didn't work well. When we come to the model 3, now what we do is to keep still the condition of using clean and generated samples from different locations, but now they are not conditioned on noisy samples. When doing this and using a spatial discriminator, The model works pretty well. We can see that more or less it can follow the sequence, but still it has some failures, or still, yeah, some of the results are a bit smooth. I don't know if it can be perceived very, very well, but at least there are some differences which are easy to perceive, some others not. And maybe on a smaller screen, or yeah, we have more detail. When finally changing the discriminator to be spatiotemporal and removing these two conditions, we achieve this sequence-to-sequence model is our proposal, and we see that more or less the sequence is pretty well reconstructed. It's true that here in the end we have still some smooth frames, but the reconstruction is pretty well compared to the other models we have seen in the comparison. The second analysis we have performed in order to evaluate yeah.
Can I ask a question about the architecture?
Sure.
Is there a reason why? So did you try also to do the temporal modeling with the self-attention, or was there a motivation to use recurrent based? Do you think it's more suited to this kind of task? Or?
We didn't get the opportunity of It's something we would like to introduce. At the moment, Maria began with her thesis. We were focused on recurrent. Yeah, her background was about convolutional SDMs. She was applying convolutional SDMs on her master thesis, so we didn't consider self-attention modules. It's something, of course, because of the literature, because they are state of the art at the moment when modeling spatiotemporal dependencies. It's something we would like to consider now for the forecasting task, but we prefer to finish.
But it could be that actually, I mean, LSTMs are slower, but the bias that they have, that the recent image have more influence on the next prediction, could be relevant for that test.
Somehow it should be analyzed the persistence of information in both strategies, because in the end it's true that we talk about long short term, but then we should see how many time steps are being taken into account for a current prediction, not only in the LSTMs. Yeah, maybe it's something it should be analyzed. I don't know if there is an analysis in the literature. I think you were working with have you been working with the gap filling model?
The cloud.
I saw it recently.
Yeah.
I saw it recently. And are you applying self-attention?
Yeah.
Okay. Yeah. I think it should be definitely. It's something we would like to consider for the subsequent experiments. Okay, so the second evaluation we are conducting is to take into account these gap fill regions at which we don't have a proper target for evaluation purposes. So what we are doing here is to rely on distribution-based metrics. We have made use of the kernel insection distance, and we are going to measure the dissimilarity between two PDF, the PDF of clean samples and the PDF of the generated samples. In order to do this, we need to extract features from the gap fill frames. And what we have done is to use a ResNet 50 feature extractor trained on bkernel. In the literature, we have seen that this kernel inception distance metric for conventional images, it relies usually on an inception version 3 model plus, which has been pre-trained on ImageNet. But here, given that we are dealing with satellite imagery, we thought that it would be more suitable to rely on a model trained on satellite imagery. This bkernel is for land cover classification. It's also Sentinel-2 images, so it's a more suitable feature extractor for our purposes. And the idea is that in order to take into account different cloud coverages or occlusion percentages, we are uniformly sampling generated samples, gap fill samples, given this noise percentage we have, or different noise percentages we have in the EarNet 2021 database. When comparing both for the IAD or OOD and OOD sets, the performance in terms of kernel inception distance, we see also that our model outperforms the other ones. Here, the lower the metric, the better the performance with this score. And also we have done this score density analysis in order to see the deviation when sampling 100 iterations by randomly selected 1,000 samples from the Univ set. We see that our model has only given these 100 iterations of the experiment or a deviation comparable to the peaks to peaks, but with the lower kernel inception distance. Here we are introducing also 3 baseline methods. I prefer to go a bit quick because I think I'm running out of time. Then if you have doubts, I can come back. And the third experiment we have done is to perform forecasting on a kernel NDVI with a very, very simple, basic linear autoregressive model, only to measure the improvement in the forecasting task when improving the quality of the data we are gap filling. And we see also, even this figure we have here, we have analyzed the Pearson correlation of the forecasting with this gap fill data compared to the original data, but masked with the quality mask in order to perform this forecasting. We have analyzed the performance, the Pearson correlation on different land vegetation classes, also in the minicubes in Europe, to see or to come up with 3 different conclusions. We see that the performance of the forecasting task when gap filling the data, it's much better in most of the locations in Europe, in 73% of the hexagonal regions in Europe. In those locations when there are not many clouds, as in the Iberian Peninsula, we don't see a lot of improvement when comparing the baseline with the gap filling. It makes sense. And also it's still a challenge, the northern European region, because we have higher cloud occlusions, so it's more difficult to reconstruct, it's more difficult to gap fill these locations. And also we have appreciate slower changes in the land cover. So when having these 2 properties, still the model or still the gap fill images, their quality is not good enough for a forecasting task, simple forecasting task, still without relying on more complex architectures for the forecasting. This is the end of the first work. I don't know if I'm going to have time to introduce everything. I will try to do my best at least. This is the second work I wanted to present you to until what time I have?
We started at like 50, so let's say 35. Like.
Okay, let me try to.
That's more 15 minutes. Yeah.
Okay. The second work I'm going to introduce is a drop detection system. It's a hybrid model. The idea is that we are combining both raw observations, precipitation and temperature with domain knowledge information provided by the standardized precipitation evapotranspiration index. What we have designed, what Monsieur has been doing as part of his PhD thesis, is also his the first part of his PhD, is this. It seems very, very complex system. Really it is, but it can be simplified, and I will see. The idea is that it's a variational recurrent neural network for drought monitoring, which is composed of 2 different branches. The first branch, X0, it's receiving the raw climate observations, precipitation and temperature. The second branch is receiving the SPI at multiple time scales. I think it's monthly, 3 months, 6 months. It's a variational approach. So in the latent representation, what we are going to do in order to guide the latent representations learned for the precipitation and temperature features for drought detection here at the output of the encoder of the first branch, in order to guide, in order to try to improve the performance of the drought detection task, what we are going to do is to minimize the divergence between the latent representations learned for the climate variables and the latent representations learned for the standardized precipitation evapotranspiration index. So here what we have is a domain knowledge prior distribution based on SPEI, which we are going to make similar to the posterior distribution we have given the climate variables. And when, yeah, sure.
Could you quickly explain how the SPEI index is computed? Because a lot of people are not familiar with sensing mathematically. Like the inputs are, because that's a drought index.
It relies also on precipitation and temperature. And what we need to compute first is the evapotranspiration. The evapotranspiration can be computed based on different strategies. We have made use of, or we have used the simplest one, I think is the Thornton-White approach, if I remember well. So based on this temperature, we compute the evapotranspiration, and then together with the precipitation, we are able, there are different probability density functions involved and some parameters. It's kind of a product of precipitation and temperature, but driven by expert knowledge. That's the idea. It's more sophisticated than only relying or only providing to an architecture input observations. Precipitation and what we are doing here also in order to simplify or in order to see the potential of incorporating domain knowledge into a deep learning architecture is to make use of an index whose input climate variables are the same ones we are using for our experiments. So both branches are receiving precipitation and temperature. On the first branch, they are not processed. On the second branch, they are processed in order to compute the SPI index. So this is a generative approach. We have different loss terms. I'm going to try to explain very, very rapidly these loss terms, given the training and test stages. As I said before, we get x0, climate variables, x1, SPI. We compute the later representations. We compute the distributions because they are variational approaches. And one of the things we are going to do is to, both are variational encoder-decoder architectures. So for the SPI, we need to minimize the divergence between the distribution of the SPI and a multivariate Gaussian, standardized Gaussian distribution. Then we are also minimizing the divergence between the latent representation or the distribution of the SPI and the distribution for the latent representation of the climate variables. And thanks to this convergence between both distributions, we are guiding the procedure for drought detection given the climate variables here and the nth. So at the output of the decoder, we are doing two things. Given the climate variables, we are performing drought detection, but also we are learning how to reconstruct the climate variables. And also in order to achieve better reconstructions, better latent representations, we are also learning how to reconstruct the SPI index. So in the end, we have three different loss terms. And we have a lambda hyperparameter here in order to measure the strength of the regularization, the strength of this divergence between the latent representation of the SPI and the latent representation of the climate variables. This is a parameter we are going to validate now. The advantage is that it's a very, very complex architecture during the training stage, but given that most of the modules being used during the training stage serve as a guidance for a better drought detection, then during the test stage, we can discard most of the modules. All the modules related to the SPI computation can be discarded. And here, once we have encoded a latent representation of the climate variables, which has been guided by the knowledge in SPI latent representations, we can directly sample from the climate variables, from the latent representation of the climate variables, in order to provide a drought detection output at the output of the encoder of the system.
Sorry,
Yeah,
I
sure.
think I understood the guidance parts, but I'm not sure I understood how you do the detection as a generative problem. So as input, you have your climate variables.
It's a supervised approach. I think I didn't mention it before. I was going to mention it. It's a supervised approach. We are relying on labels.
Okay. And so you have your autoencoder that just processes the climate variables, and then in the decoding part, it just predicts it's a binary classification, or
it's a binary classification.
Okay.
We are addressing drought detection as a binary classification task based on the labels on the geocode disaster database. I don't know, have you heard about the geocode disaster database?
No.
It's an extension of the International Disaster Database. Maybe you are familiarized with the International Disaster Database. It's a register of the database of a lot of streams worldwide. We have drought annotations. And this extension, it provides us is with polygons, with administrative polygons. The International Disaster Database, for each of the stream events, for each of the drought, it provides a list of locations at which the drought has happened, the drought event has happened. All these locations can be rasterized in order to provide polygons to highlight those locations with the label equal to 1. So in such a way, we are addressing drought detection as a binary task. 1 equal to drought, 0 equal to non-drought. The issue here, or the challenge with these labels here, is that the labels are noisy or are weak in the sense that they correspond to administrative boundaries, but they don't exactly correspond to those locations affected by the droughts, because we don't know exactly which locations administrative boundaries are standard or are a convention, but they don't correspond with the affected areas. So it's a good proxy, it's a good reference in order to train a supervised system, but it still has some issues when dealing with. So we have 3 different kinds of information: the climate variables, the SPI index, both as input, for both branches. And in order to learn the drought detection task, we have this binary information in the International Disaster Database. So this is what I was going to mention here. This is the list of European events we have considered for our experiments between 2003 and 2018. This is the training validation test split we have considered. We have performed experiments on individual events on different countries, but also experiments at the whole region of Europe in order to measure the performance at the global or by considering a generic European setup. These are the conditions the international disaster team is following in order to annotate, in order to register an event. A stream happen if it provides or it's related to 10 fatalities at least, 150 people, or it involves a state of emergency or a call for international assistance. To simplify also the scenario, the training sampling strategy, the issue also when dealing with droughts or when dealing with streams is that the probability of having a stream is very, very low. So somehow we need to balance the number of samples for streams and the number of samples for non-streams. In order to slightly increase the percentage of locations affected by the stream with respect to the total number of locations considered for the experiments, we are considering only for training drought-affected locations. Countries or locations in Europe at which at some point, at some time steps between 2003 and 2018, a drought event has happened. This is the validation of the lambda hyperparameter in order to see how should be the strength of this regularization term depending on the domain knowledge we have when training the architecture. We have seen that depending on the event, the lambda parameter is slightly different. So we have come with the lambda parameter equal to 0.01 for all the experiments, which is a balance between the validation we have accomplished with all the events available. Here we have the 4 events in the test set: Afghanistan, Italy, Moldova, Russia. And we have also 2 scenarios. Europe 0 is evaluating the model in those locations at which at least a drought has happened during the whole time period. And Europe 1 is when we are evaluating the model at the whole region of Europe, not only on those locations, but considering also locations at which no streams, no droughts happened. These are the results. We are also performing a comparison with a kind of an ablation study in order to simplify the whole domain knowledge-driven variational recurrent network architecture. We are using the variational LSTM, but without using this domain knowledge provided by SPI, variational multi-layer perception, an LSTM, and a multi-layer perception without the variational approach, without this latent space defined by the mean and equivariance matrix.
So what is the contribution of the guidance with the pullback live divergence between the 2 distributions?
The idea is that we are able to improve the performance of the drought detection task, given that we are learning. Yeah, sure.
In terms of numbers.
In terms of numbers.
Yeah.
Our model is the black bar.
Okay.
So we see that not in all the cases, I have to say, but in most of the cases we are improving the performance of these simplified approaches. It's true that when dealing with drought detection at the moment, given that there are not a lot of works in the literature, it's difficult to compare or to demonstrate the performance of our systems. That's the reason we have defined simplified models for the comparison. We see that for the case, these are 2 experiments. The first experiment, which is about the drought monitoring, we see for the different events and for the European scenarios that our model outperforms, not in all of them, I think it's in all of them, except for Moldova. Moldova is a special case at which this LSTM model performs better. It's something we should analyze. It's still not analyzed. This is the performance in terms of area under the curve, precision recall, and F1 score. Here, the advantage of these experiments is that given that we are dealing with the recurrent architecture and the training, validation, and test split is subsequent, so the training set is prior to the validation set, and the validation set is prior to the test set, we initialize the hidden states of the recurrent architecture to the first or to the last time step in the prior subset. So here we see an advantage in terms of performance when looking at the numbers. In this second experiment, we are performing a cross-validation test. We assume 3 independent subsets, and we don't initialize these hidden states to the hidden state we have at the last time step in the prior subset. So when doing this, the performance decreases, but still our model outperforms the other models in the comparison.
And so you call your model DK, so domain knowledge? Like
DK, yeah.
Because you use the SPI as input, right?
That's it.
And so for the other models, the RNN and the VNLP and the VLSTM, you do not use the SPI as input.
We are not considering SPI in these models.
Okay, but what are you using as input?
Only the climate variables, only precipitation and temperature. It would be
okay.
only you to get an idea, it would be only this first branch, being variational or not, without considering the second branch, which is about the SPI, but still using the precipitation and temperature features.
Okay, but what would happen if you would just use the SPI as input to just one branch? It's just no generative approach, just generative.
We have the results as well.
Okay.
let me. Here they are.
Mm-hmm.
This is what we are doing in this generalization analysis. It's one of the things we thought, okay, at the moment we are combining the climate variables with the SPI, but using 2 different branches with a variational approach. But what if we simply use the SPI index as an input? Or what if we simply use a concatenation of the climate variables and the SPI? It's something we could do instead of designing this very, very complex architecture in order to perform drought detection. This is what we have studied. We have analyzed here. We have 6 different models followed by our approach, again in black. This is recurrent neural network or LSTM. In the end, these are similar approaches. And one of the models is receiving only SPI features. The other model is using the climate variables, I think, SPI, the concatenation of the climate variables and the SPI. And finally, the third model is using, let me remember because there are many experiments, sorry. SPI input features, concatenated, and the standard is only the climate variables. So climate variables, SPI, model only with climate variables, model with only SPI, and model with the concatenation of climate variables and SPI. And finally, our model in black, which is the 2-branch variational approach. And we see that for all the, I think, in this case, for all the events regarding the 3, no, still in Moldova, we have the exception in area under the curve and precision I recall, but looking at least at European level, we see that the way of combining these 2 informations by means of the variational approach, by means of this divergence, minimizing this divergence between later representation, it seems to work.
I'm going to finish
the part. I think I should, sorry. I have still a third work, but no worries, I will finish with the presentation. Then if you are interested, we can continue the discussion. Sorry, because there are many slides, and I think I didn't prepare it very, very well. This is an ablation study on the lost terms. These are the qualitative results. Here, what we are doing is the temporal aggregation through time by computing the average for each of the locations for Afghanistan and Moldova in order to see the drought detection signals through time. And here we see the SPI 6-month index followed by the maps provided by our variational approach, but without domain knowledge and the domain knowledge proposal. The advantage being a variational approach is that we are not only provided in the first row the probability maps by highlighting those locations affected by droughts, but also we can compute by replicating multiple times the experiment. We can compute uncertainty maps in order to see how certain is the architecture when providing these predictions. That's another advantage when dealing with a variational approach. I have a third work I'm not going to present because I'm running out of time. This is my research on unsupervised drought detection. It's still ongoing, so I hope I can present it to you at some point. here they were the animations. They were not necessary. An explainable AI analysis we were doing for this case study on the Russian heatwave. In case you are interested, please feel free to ask me afterwards. And this is the IDE toolbox we are implementing. The first version is already available in GitHub. It's a generic framework for stream event monitoring. It's a simple pipeline, and the objective is to have this pipeline. Hope it can be helpful for climate experts or for machine learning experts in order to solve different case studies on extreme event detection. Not only on detection, but also on characterization and impact assessment. We have some modules in order to address all these tasks together by simply defining a dataset class in PyTorch. That's all. I was going to finish with some conclusions on the different works. Again, the challenges, I think these are conclusions, still ongoing work in order to continue with the stream event monitoring. These are the references of the works, and these are the acknowledgements, the projects we are involved. We are dealing we are part in order to do this research. Also, the computer resources provided by Artemisa. This is very important. Without GPUs, it's very, very difficult to accomplish or to do experiments with these complex systems. And that's all for me. Thank you so much. Sorry not having more time, but thank you so much again for the invitation.
Thank you. Thanks a lot, Miguel, for the presentation. And yeah, I'm curious to learn more about the last parts or the teasing. So we have time for like 5 minutes of 5-10 minutes of question on what we've heard or what we didn't hear, what we didn't hear.
I have a question.
Sure.
It's probably a naive one, but when you have the temporal sequences, what time frame is that? Is that like minutes or days? Or...
That's an important thing. Too many details during the presentation. Sorry, it depends on the setup. On the first part, for the satellite imagery, for the Earth surface gap filling, we have 5 days resolution. So the resolution is 5 days for Sentinel-2. For the case of the second work I presented for the drought detection is weekly. It's 8 days. It's 8 days. So we are providing a prediction every 8 days because of the resolution because of the nature of the data we have, the climate variables or the satellite imagery for the first part.
I have a question on on the last pitch you presented you were saying that the interest of the variational model is also that you can predict distribution, so you can have uncertainties. Did you measure a bit if the uncertainties are calibrated?
It's something we are doing at the moment. Okay. It's the subsequent stage. On the thesis, Monsieur is working on these experiments. It's something I have here annotated. The uncertainty analysis. Now what we are doing is, given that we have this system implemented, and in principle it works well for drought detection, still it has some drawbacks, but it works reasonably well. We are analyzing the uncertainty of the model depending on the data source, because the precipitation and temperature variables could come from different sources. Also about the training strategy, the way we are sampling. These are LSTM models, so these are pixel level. We don't have spatial dependencies, it's only temporal. So the way of sampling, the way of providing each of the time series or the model, or maybe training a model on a specific location and then trying to extrapolate in order to see if it works well or not on other locations, or we should adapt it based on a lot of samples or based not on many samples. These are things we are trying to do at the moment in order to get a better idea about the performance. Of course, it's one of the things I mentioned before. It's very important to evaluate properly everything in order to also, it's as important or even more important than the explainability, because in the end, yeah, sometimes the scores are not very meaningful. So somehow we have to take is what we were seeing on the first part of the presentation. We have to take multiple perspectives of evaluation in order to be sure about the performance of the system. We'll do it. We are currently doing it. Yeah.
Can I'm completely out of the field, so that's more like this. So is height playing any role in your? Are you using the height, because I guess that determines for the droughts?
I
Using
think,
like the
Elevation.
the elevation,
Yeah.
sorry.
not at the moment as a feature. It's something we could consider indeed. But I don't know if it's a feature we have in this database. Most of the times we are not using features because we lack of, my background is on computer vision. So I'm still learning from my colleagues in order to get a better idea on remote sensing, on the definition of these streams. But sometimes it's also about the availability of data. The last of my PhD students, Jordi is also working on supervised road detection, but modeling spatiotemporal dependencies, also relying on the International Disaster Database. And one of the things we wanted to do with his thesis is still ongoing research. That's the reason I didn't present it here today. It's a context-aware or location-aware model at which we are not only taking into account climate variables, but also soil properties in order to contextualize, in order to guide a little bit better the performance of the model depending on the soil properties. And the elevation, I think it was one of the features we had, but not completely sure. Of course, I think it should be, yeah. All features are not only for the prediction, which could be improved, but also for the understanding on how the events are having an effect.
Yes, actually 2 questions. So about the Earth filling gap project. So one is it intrinsically more difficult like to deal with some kind of environment with respect to others? So I would expect, for instance, a uniform flat part, it's easier to handle than the Alps, for instance.
I think so. In the end, when performing experiments, we rely on the minikubes available on a particular database. So depending on how they have been sampled, we have more challenging or less challenging scenarios. But of course, it depends. More homogeneous areas is going to be easier to capture them. And if we have more specific details, like in buildings, or maybe it's going to be more difficult for the architecture, at least if it hasn't received that information in advance. If it has received that information and it has encoded properly the information in order to retrieve it at the moment the gap fill should be done, it could work. But it's true that for some patterns, for some specific land covers, maybe we don't have tons of examples in order to model them properly. So of course, and this is something we should also consider for evaluation purposes, because there are some minikubes or some patterns or some locations which are more challenging. Somehow we should pay more attention. At some point, I suppose these gap filling techniques will convert to very, very high performance scores. It's what usually happens in other computer vision tasks. At that moment, in order to really evaluate the performance of the models, we should pay attention particularly to those very, very challenging minikubes in order to get a proper idea about the quality of the models. Still, it's true that about gap filling, there are more works in the literature, but at some point it's true that they will converge to very, very good performances. And maybe this is real or maybe not, depending on how we have evaluated the systems.
Okay, but second question is, I understand that you essentially the technique of gap filling is then used to polish the training data set to then be fed to another neural net, right?
That's our purpose. I don't know what, it's something because the paper has been just submitted. So we are thinking about how we are going to continue. The original plan was to try to integrate both systems, the gap filling system and the forecasting. In the end, both tasks, somehow they are related to each other. The thing is that, in my opinion, the gap filling task is easier because you have more contextual information. It's only completing those missing parts. For the case of the forecasting, we have to anticipate the future. We have to predict whole samples, and depending on the persistence of this information and depending how it changes, of course, it's going to be more challenging. But somehow both tasks could be addressed with similar architectures.
No, then my question, you probably still don't know it, but was like, is there the possibility that the second net, taking it as input the results of another net, is kind of tricked by the fact that it has got somehow polished by AI as well, like the training data set?
Of course, and if the performance is not good, we are propagating errors, and how we should measure also how errors are propagated. We need to be careful when concatenating systems, of course.
So we had also worked in our team a bit on the cloud removal with some Univ colleagues, and the question that came back to me always was, why do we actually do that? What's the application in mind? Because like for land cover classification, any sequence model would learn to ignore the cloud styles. So what, from your point of view, if we do now manual interpretation of all the single images, right? Because then we just take it one without nodes. So what is the application? Why do we actually split this task into? Why not use the raw data input and learn our final application directly?
That's a good question. Indeed, forecasting have been addressing on the first works without taking into account gap filling. That's a very good question, because in the end you could always, our ultimate goal was to perform forecasting. Our subsequent task, of course, there could be another tasks, but our subsequent task was forecasting condition on streams. Forecasting has been addressed in the literature by using data quality masks in such a way those pixels which are missing or those pixels which are occluded, they can be removed when backpropagating, when computing the loss, when backpropagating the gradients to update the weights. So it's something we could do, but it's true that the quality of these masks is not usually very good. Of course, I think in that regard, there are different ways of addressing, because one way could be, instead of performing the gap filling task, to try to improve these quality masks, or maybe to perform cloud detection, and when having a better quality masks, to make use of these quality masks for the forecasting task. That could be another possibility. I don't know. I have to say that also when we were designing this pipeline, somehow we think also in try to in the end it's a PhD. Somehow we want, in a PhD, we want to do research, but it's also important for the students to learn different methodologies, different ways of evaluating. So maybe the reason we made this decision was also about Maria's PhD, also to take the opportunity of dealing with different approaches. I don't know. In the end, still forecasting is being addressed with these data quality masks. Maybe it's not completely necessary for the subsequent task. It's something we should evaluate at some point. By using the same architecture, but providing as input these gap fill images, or by providing as input the occluded images, but with the data quality mask, to see which one performs better. I'm not completely sure. Maybe it's not necessary, but I don't know. The reason was to try to have a plan for her PhD. That was the main reason. Yeah.
Maybe, I mean, one application is to apply, if you're gonna use tools that are not deep learning or machine learning, like for example NDVI analysis, where you're just gonna compute your index and do some simple thresholding on that, because for example you don't have a lot of training data.
Yeah, my point is just that we are hallucinating pixel values, right?
Yeah.
We're trying then to, based on the hallucinated pixel values, do physical measurements. That's the point I'm seeing.
Yeah.
I think to remove clouds implicitly, and you split this explicitly into different steps, that you might be able to work with smaller networks and smaller training data sizes. But there's other questions that come with it, because we are hallucinating new. It's not even a simple interpolation, really, or nothingness. Right?
Yeah, there is more to.
I think it's very interesting. But Vivian and I, we have been discussing.
Yeah.
If you are concatenating architectures, you are increasing the complexity of the models, and how you should try to take advantage of one of the modules to try to integrate both tasks at the same time, still using the same architecture to simplify. Yeah. That's important as well.
Okay, I think I will leave it there. Thanks again, Miguel. Bon appétit.
Bon appetit. Thank you. Sorry.
No worries.
Yeah, too many details. I wanted to. I always have this same issue. I had to practice more the presentations, because I think
Yeah,
I'm
there's
going
a
to be
lot.
able to cover a lot of